Hi all, I'm your TA Balaji and today we will be discussing the solutions for assignment 8. Question 1. Consider the Boolean function f of ABC such that it is this, right? And does this function obey the mirroring property? So to determine if a function obeys the mirroring property, you need to check for this condition, which is f bar of a bar b bar c bar, that is the complement of all the inputs complemented must result in the same value as that of f of ABC. So in this case, the complement of the individual values a bar, b bar, c bar would give you this new minterm 0653, whereas the original minterms was 7124. If you write this as minterms. Now, if you go back and try to find out f bar's minterm, which is the complement of this, that will be 1, 2, 4, and 7, which is exactly the same as this. Therefore, the mirroring property holds. The exactly, a similar kind of logic you can apply even while, looking at the truth table, and it will be more intuitive if you analyze this by writing the K map and looking at the truth table, right? If you look at the truth table for where you can write A, B, and C, and you write F, and you write down its truth table values, and you look at again a bar, b bar, and c bar, and again look at that truth table values, and then f bar of a bar, b bar, c bar, and that values, you will really be able to appreciate this mirroring property, right? So that's question number one. Question two, consider the Boolean function f of ABC again with this formula. Now to check if any particular function does obey the mirroring property, all that you need to do is write down the property, the write down in min terms and check for the condition f bar of a bar, b bar, c bar is equal to f of ABC. So in a very similar logic, it does match up, which is 7356 is again 3567, which is exactly the same in terms, and therefore this function also obeys the mirroring property. Going to question numbers 3 to 7, for which the common data is here. First of all, for a pseudo NMOS inverter, so pseudo NMOS meaning the PMOS over there, right, is whose gate is tied to ground. Its VOL is equal to 0.06 volt. What should be the WN by WP ratio? Uh, Assume that the devices are of minimum length and short channel effects of velocity saturation exists, but other effects like dibble and channel length modulation do not exist, right? So with such assumptions, we can safely assume that the NMOS is in linear mode because its VDS is very low, which is 0.6 volts, and the PMOS whose VDS is or VSD is very large can easily, you can assume it to be in velocity sat, because would have been in sat if it was a long channel device. Otherwise it would because it's a short channel device, it's safe to assume it's in velocity sat. So when you write down this and write down the expressions and match the currents and solve for WN by WP, which is what is asked, you will get this expression. So I'll just give you a minute to look at the working. So you start, you equate the terms, and this is how you get it. So 3.284 is the answer we're looking for, right? Now, question number 4. So, assuming that Wn by Wp is found from question 3, right? So, Wn by Wp is a particular value, which is 3.284. Now, for questions 4 and 5, let's assume that the size of the PMOS is alpha beta and that of the NMOS is beta. In some way, we are saying that Wn by Wp, which is 1, is equal to 1 by alpha, is what is known from here. That is, we know what is the value of alpha. We know that alpha is equal to this value, which is 1 by whatever we found out earlier in this question, right? Now, we need to find out what is the exact value of Wn and Wp. That's why we are going through this. So we have, two variables. We have one equation, which is, we got to know what is the value of alpha, but we need another equation to solve for uh, beta, right? We need a relationship between alpha and beta. So for that, let's look at the current equations, right? So here, assuming that I is the current, that is the current through the uh, discharging capacitor, right? So the capacitor provides the current coming from here is I, let's say, and the current coming from the PMOS is alpha beta by 2 into I because of its sizing. So when you add this up, that is the total current that goes here, which is by KCL. So the current I is equal to this value, and in such a way, if you go ahead and proceed, you will obtain the relationship beta is equal to 1 divided by 1 minus alpha by 2, right? So in solving for beta from alpha, you will get this. Now, since beta is exactly the size of the NMOS, you now know the size of the NMOS. And alpha beta is the size of the PMOS, therefore you know the size of the PMOS as well. Therefore, these are the values that are expected for question number 4 and 5. Now, question number 6, assuming that W1 and W3 in question 4 and 5, calculate the pull-up logical effort. So, question number 6 and 7 are exactly uh, no, question number 6 at least, right? Is the find the pull-up logical effort (GPU). Now the pull-up logical effort will be dependent on the reference inverter whose sizing for the pull-up is that of this, right? This is the sizing because that's what will help you pull up, and the sizing of the capacitance of the input of which is connected to A is always fixed at 1.1795, but the reference inverter must be in with respect to the pull up that is being used, right? Because you are supposed to transition from 1 to 0 for the output to transition from 0 to 1. Therefore, in such a way, the GPU is 2.1903. Question number 7. As a designer, you face the problem of building a NAND 2 with the following design constraints. The system is such that the input always rise during evaluation. Ensure minimum delay and moderate area implementation with frequency support of greater than 10 gigahertz and no static power consumption. Select which logic you would use. So, you would use domino logic. Uh, the reasoning for that would be that the NAND 2 gate, the system it supports a frequency of about 10 gigahertz, right? So that is it says that it is supporting high frequencies, and it says there's no static power consumption. So that means there is no pseudo NMOS logic cannot be used. Okay, then you're saying this is such that the input always rise during evaluation. So since it's only rising during evaluation, you could go with a domino setup where you can always prioritize the rise, right? mm. Ensure minimum delay and moderate area implementations. So the best delay the best delay for only rise you can really optimize by going to for domino logic, as you will be sizing all the gates of the domino logic in such a way that the rise is favored, right? In CVSL and static CMOS, you will have to look at both rise and fall, for which you'll do some particular sizing. But for the domino logic, you can go as close to G equal to 1 for rise. Okay. Question number 8. What is the fall logical effort for any input in a dynamic footed 8 input NOR gate? Okay. So question number 8 asks for a dynamic footed 8 input NOR gate. Right. So this is your NOR gate. You're using 2 here because it's a footed NOR gate, and the reference inverter over here for the fall is the standard reference inverter, which is 2 and 1 sizing. 2 divided by 3 is your fall logical effort. What is the fall logical effort for any input in a pseudo NMOS 2 input NOR gate? Now again, when you say pseudo NMOS, you will say that let's say you've chosen a sizing like this, then the reference inverter, right, that you will be using should have that of uh, and this is for the fall, right? It's not for the rise. So you will be using the standard reference inverter, which is 2 and 1. Therefore, your GF is equal to 4 by 3 divided by 3. 4 by 3, since A is equal to, you're using the standard 4 by 3 sizing, 4 by 3 divided by 3. Therefore, 4 by 9 is your answer. Now, questions 10 to 12 will have this as the base circuit, right? Question 10. Determine VIL of the inverter, such assume the noise margin model for the margin approximate model for the calculation, right? So for question 10, we are asking to find out what is the value of VIL. So VIL from the noise approximate model is given by Vm plus VDD minus Vm by G. So all of these values are given to you. Vm is VDD by 2, VDD is 1.5, Vm is 0.75, G is minus 13. You can find out what is VIL from it. Moving on, what is VIH? Again, from the same approximate model, VIH is Vm minus Vm by G. All of its values are given. Therefore, it is 0.80769. Finally, let Wk equal to A8. Assuming there is no channel length modulation and dibble, determine the node voltage of out just before the falling edge of the evaluate mode. And assume node A is held at ground for this calculation. So, if you were to assume that node A is held at ground, go back to the diagram, right? Node A is, grounded. Okay, so you're now being asked what will be uh, determine the node voltage of out just before the falling edge, right? So you're supposed to find out what is the value of out, right? So to find this out, you can write such an equation, right? Where, uh, for the NMOS, which is pulling down, which is this NMOS, you can assume that you can write an equation where the Vs is 0 and Vg is VDD, and your Vs is 0, Vd is V naught and V naught. So you can assume this to be your NMOS, and now for your PMOS again, you need to assume that VDD, this is VD, I mean, all of this in mod terminology, VDD minus mod VT minus VDD minus V naught by 2. So basically, take this particular PMOS and write down its expression, right? Uh, now, once you solve for V naught and you obtain this as your V naught, uh, with Wk equal to 8. So you've been given what is the value of Wk, right? That is given as 8. You will be able to, and Wn, for example, is you start with 2. Wn is 2. So therefore what you would have done is 2 and 8, which is 4, and carry on, use that value and use VDD, VT, value to solve finally for V naught. Everything else is given to you in the common data, right? So finally, when you solve for V naught and you get 1.17 volt, it's exactly what is expected over here. Thanks, guys. If you have any questions regarding the solution, please post your questions on the discussion forum. Thank you very much.